oxygen reacts with the silicon surface in a hot furnace to grow a thin layer of silicon dioxide. This process is similar to the way the sun's heat and the air's oxygen turn the shiny new paint job of a car to a dull coat over the years. The silicon dioxide layer will be etched and used as a stencil to dope specific regions of the wafer. But first, the pattern for the stencil is applied to the silicon dioxide through a photographic technique called photolithography. The first mask pattern will be transferred onto the wafer using photoresist, a material which is sensitive to light. In slow motion, we can see the thick photoresist, which is a resin dissolved in solvents, evenly spread over the surface. The wafers transfer to heating plates and bake at low temperatures to evaporate the solvents, leaving a thin layer of resist. The wafer then enters a computer-controlled machine called a stepper. Inside, the wafer is positioned underneath the selected mask pattern. Ultraviolet light exposes the pattern across the surface of the wafer. In this way, many chips are made on a single wafer. By increasing the diameter of the original crystal, larger wafers are sliced and more chips can be made on each wafer. The wafers are then developed. There are two types of photoresist, negative and positive. A negative resist hardens when exposed to light and remains on the wafer when developed. In this run, a positive resist is used. When exposed to light, the resist changes chemically and is removed when developed. The regions of silicon dioxide, now unprotected by photoresist, are then etched. Although acids can be used for etching, most wet chemicals etch in all directions at equal rates, which can result in undercutting of the photoresist. Undercutting could create an inexact transfer of the mask. When a critical fine etch is needed, the wafers undergo a dry etching process called plasma etching. In the plasma chamber, a chemically reactive gas provides free fluorine atoms, which react with the exposed silicon dioxide to leave sharp vertical walls. High magnification SEM photographs show the precision of these etched regions. The hardened resist is then removed in a dry process, using oxygen plasma, which may include fluorine, followed by hot acid baths. This leaves a stenciled silicon dioxide layer as insulation. Photolithography will be used with each of the subsequent masks in the process. This technique allows us to isolate microscopic regions of the wafer and construct them into components of the electronic circuit. In this way, the transistors and circuits are gradually built, a layer at a time. In the ion implanter, dopant ions will bombard the wafers to create N-type regions. The depth of the ion implantation depends on the amount of energy used. Dopant ions are separated from other elements and accelerated to high velocities in a strong electric field. The ions are then driven into the wafers, implanting the exposed silicon regions. The silicon dioxide layer on the wafer blocks the dopants from unwanted regions. Because these wafers are p-type, phosphorus ions, which are n-type dopants, are implanted. Exposing the wafers to high temperatures diffuses the ions deep into the silicon substrate. This creates a well of n-type substrate where the p-channel transistor will be built. If the wafers were n-type, then boron would have been implanted to create p-wells. A new thinner layer of silicon dioxide is regrown, and its thickness is carefully monitored and measured. In a deposition furnace, a layer of silicon nitride is deposited over the oxide layer. The nitride layer prevents additional growth of the silicon dioxide layer and protects the region where the transistors will be built. Photoresist is again evenly spread on the wafer and baked in preparation for the next mask. Using a computerized machine, each new mask is perfectly aligned to the pattern already on the wafer. The second mask, used to define the actual transistor regions, is also exposed across the surface of the wafer. The wafers are developed to remove the exposed photoresist, then rinsed and baked. The wafers are then plasma etched. The free fluorine atoms react with the exposed nitride. After the photoresist is removed, the wafers go back into the oxidation furnace. A thick insulating layer of silicon dioxide, known as field oxide, will be grown where the nitride has been etched. To grow these thick layers of oxide, oxygen combined with hydrogen is introduced on the wafers as steam. This insulation reduces the electric fields between the surface and the underlying regions. Through the microscope, the field oxide looks like white boundaries. It will block the current from leaking between devices, allowing thousands of transistors to coexist in a small area. The remaining nitride layer is then removed by a combination of dry and wet etching. The wafers are then implanted with boron ions, which penetrate the silicon substrate only through the thin oxide layer. This provides uniform electrical characteristics in the regions where the transistors will be built. This thin oxide, which may have been damaged by the implantation process, is removed, and a new layer of silicon dioxide is grown in the gate area. In the vertical furnace, the gate electrodes will be formed by depositing polysilicon.